Okay, we're going to look at our imaginary numbers now. We've already done a little bit of this with our simplifying the square roots, but let's formalize some stuff and solving equations with it as well. So first of all, we've got some real solutions to an equation like this. And if we recall from earlier in the year with functions, this graph looks like this. It's an x squared. Remember, this means it's been shifted down 4. And what happens is we see that it's got x-intercepts here and here at x equals 2 and negative 2. Those are also the solutions, right? If you solve the equation, if you make y equal to 0, because remember these points are negative 2, 0, and 2, 0. That means if you plug in 0 for y and you solve, so how would we solve this? We could factor it, of course, but we're going to do some isolate the variable stuff here. So if I subtract 4 off both sides, I'm left with x squared, or add 4 off on both sides. I'm left with x squared equals 4. Then if we square root both sides, no problem. We can square root that 4 and we get 2 or negative 2. And that's what x is equal to. All right. Oh, I should say we actually talked about this. There's a step in between there. When we square root the x squared, we get the absolute value of x. When we square root 4, we get 2. And then that means that x is equal to 2 and negative 2, which I have below there. All right, so no problem. Now we look at this one, x squared plus 4. That's our parabola that's been shifted up 4. And what we notice is there's no x-intercepts. So what does that mean? That means there is no x value that when we set y equal to 0 that we can solve. So if we try and solve this by isolating the variable, we subtract 4 off both sides. We're left with x squared equals negative 4. And then, we square root both sides, and we get the absolute value of x equals the square root of negative 4. We've said, oh, we can't square root a negative, right? So that's why there's no solutions. Well, there's no real solutions. This x-axis is a real number line, and there are no real solutions to this. That's why there's no x-intercept. But we now know that the square root of a negative can be done if we make it an imaginary number. So the square root of negative 4 is actually 2i. And then when we have absolute value of x equals 2i, then we know x is equal to 2i or negative 2i. And that's how we get our imaginary solutions. Notice, though, the connection for imaginary solutions into the graph. There is no x-intercept. Only real solutions provide x-intercepts. Okay, so now we have our real and imaginary numbers. Just some review of how to simplify a radical. This one is a perfect square, so I can just say the square root of 36 is 6. This one, I would break it down into negative 1 times 25. Anytime there's a negative under the square root, we're going to do it this way. The square of negative 1 is I. The square root of 25, well, that's a perfect square. So the answer to that is 5i. We don't do negative 5i because we're not solving an equation. We're just taking the square root of that number. So the thing here to remember is whenever you have a negative under the square root, another way you could look at it is you could just pull the negative out as an I and then make the square root positive and then continue simplifying. So some things about imaginary numbers. We know that I squared is negative 1. So then we square rooted both sides and we got that I is the square root of negative 1. All right? And so we're going to look at what would I to the third be? Well, I to the third can be written as I squared times I. And then we know I squared is equal to negative 1 from above times I. So then when I multiply those, I get negative I. So I to the cubed is equal to negative I. Whoops. All right? So, oh, and by the way, up here we're saying the square root of negative 1 is actually just I. All right, actually, I'm going to write that underneath because I want to keep this like clean here. So it seems pretty obvious that I is equal to I. But you'll see what's going to happen here in a second. Then I to the fourth, I would break that into I squared times I squared. And that would be negative 1 times negative 1 because I squareds are equal to negative 1. And then negative 1 times negative 1 is 1. So we were saying it's pretty cool that I squared is equal to negative 1 because when we were doing multiplication, we would say anytime we got an I squared, we can change it to the real number negative 1. Well, I to the fourth is kind of even cooler because not only is it simplified to a real number, it's actually just positive 1, and when you multiply by positive 1, that doesn't change anything. So we're really looking for I to the 4th if we're simplifying i's to larger powers. Now what happens with I to the 5th? I to the 5th would be I to the 4th times I to the 1st. So I want to break it into how many sets of I to the 4th can I have, because I to the 4th is equal to 1, and then 1 times I is just I. All right, I to the 6th can be written as I to the 4th times I squared. I to the 4th is just 1, and then 1 times I squared. So you see when we break off a set of 4 i's, it's just times 1, which doesn't change anything. The answer will be just what you have remaining after you break off a set of I to the 4ths, right? Because I to the 4th equals 1, and 1 times anything is itself. So once you break off that set of I to the 4th, you have I squared left. So I to the 6th is equal to I squared. We can do this with any power of I. How many sets of 4 are in I to the 15th? I to the 4 times I to the 4, that's 8, times I to the 4, that's 12. Then we have, what, 3 left over? So all of these equal 1, 1, 1, and 1 times 1 times 1 times 1. It's all just 1 times I to the 3rd equals I to the 3rd. So what we can do is, instead of figuring out how many sets of 4 by writing it all out, you could take the number 15 and divide it by 4. And then just look at the remainder. We don't care about how many sets of 4 there are. There were 3 sets of 4, right? We didn't care about these 3 sets. So we don't care about the quotient. We just care about the remainder. That's how many i's are going to be left over after you take out all your I to the 4s. So right here, if we do 34 and we divide it by 4, we're seeing how many sets of 4 are in 34. I'm going to say 8 times 4 is 32, and the remainder is 2. So this will equal I squared, because the remainder is how many i's are left. This is just saying there's 8 sets of I to the 4th, which just equal 1. Because I to the 34th could be I to the 4th times I to the 4th times I to the 4th times I to the 4th, right? That's 4, 8, 12, 16 i's, and we can keep going. 20, 24, 28, 32, and then we have 2 left over. That's what's happening when you do the division. Notice there's 1, 2, 3, 4, 5, 6, 7, 8 ones. 1 times 1 times 1 times 1 times 1 times 1 times 1. We don't care about those. We don't care about how many sets there are. We just look at the remainder. There's 2 left over, so it's I squared. All right, moving along. Simplify the following, classify as real or imaginary. So whenever we have a negative, we know that it's going to make an I. So I just start off by doing that. I'm skipping some steps here. We just kind of know that that's the case now. Now I work on simplifying the square root of 40. So I know that in perfect squares, I can write it as the square root of 4 times the square root of 10. And the square root of 4 is 2. And the square root of 10 can't be simplified any further. So I've got 2i root 10. All right? And by the way, that's an imaginary number because it's got an I in it. 3i times 5i. When I multiply, I can multiply the numbers. I get 15. I times I is I squared. Then we know that I squared is equal to negative 1. So 15 times negative 1 is negative 15. That's our answer. And that is a real number. It has no imaginary part. Okay, so that's kind of cool to show that when you multiply, this is an imaginary number, and this is an imaginary number. And when you multiply 2 imaginary numbers, it's possible to get a real number. Okay, so then if we look at I cubed plus 3i, well, we know from our chart up here that I cubed is equal to negative I. So we have negative I plus 3i, right? We can convert that there. And then that's kind of like, I'll just rewrite it like this. It's like negative 1i plus 3i. So whenever we have higher powers of I, we're trying to convert it back to one of these 4. It can always equal one of these 4. So I can add these together just kind of like x's, right? So negative 1 plus 3 is 2i. And that's an imaginary number because it has I in it. My iPad freaked out there for a second. Now we're going to use this to solve quadratic equations where we can isolate the variable. That means get the variable by itself. Right here, we're going to divide by 2 on both sides, negative 2 on both sides. Over here, we get n squared. Here we get negative 9. Now we're going to square root both sides. And we're going to get the absolute value of n equals, oh no, now we're trying to square root a negative number. Well, I can make it an I, and now just think of the positive 9, so it's going to be 3i. And then the square root of n equals, the absolute value of n equals 3i, so n equals negative 3i or positive 3i. Not right now, sorry, I'm making a video. Thank you. Okay, so that's how we solve those. I skipped a bunch of steps going from here to here, but you should be able to figure those out. If not, you can ask me in class. That could be something you could ask about. So here we're going to isolate the variable, so we want x squared by itself. We're going to subtract 1 off both sides and get here. Once again, we square root both sides, and we come across this square rooting a negative, which in the past we've said, oh no, we can't square root a negative, right? Well, now we can. We just call it, it's an I, and we can lose the negative part. So now I'm just thinking, what's the square root of 7? I can't simplify it, so I'm going to leave it like that. We always write the square root number last, so there's no confusion about what's underneath the square root, okay? And if the absolute value of x equals that number, then x will equal the positive version of that number or the negative version of that number. All right, we'll do the same here. These are kind of the same thing over and over. I'll let you try this one on your own. You could check with me. Oh, it doesn't even equal anything, so never mind. We won't even do that one. Let's move down to these guys. So here, first I want to get rid of the square. So we're going to square root both sides. And we're going to get n minus 1 equals. Now we're going to drop the absolute value part here. It's just easier to think like that we already have 2 solutions. So, well, I guess we could do it. We'll say the absolute value of n plus 1 equals 5i, because that's the square root of negative 25. Now, if we know the absolute value of n minus 1 is that, we know that n minus 1 equals 5i, or we know that n minus 1 equals negative 5i. That's also kind of, there's also more we should really do with this, but I'm going to leave it at this for now. So now we have 2 different equations we have to finish solving because the absolute value doesn't get us right to our answer. Now if I add 1, I get that it's 5i plus 1. If I add 1 to both sides. If I add 1 to both sides here, I get 1 minus 5i equals n. Or I could write it as negative 5i plus 1. I kind of like writing them both as the 1 first. So let's rearrange this one. We're going to say this one, we'll rearrange it as 1 plus 5i. Then you can see that they're conjugate pairs. 1 plus 5i, 1 minus 5i, conjugate pairs. That's going to be a thing for us. We'll talk about that later. And by the way, these are imaginary, or we can call them complex. All right. We will do. Let's finish these in class.